Welcome to Math with Professor V. In this video, I'm going to solve the most recent exam. I gave my Calculus 3 multivariable calculus class summer 2025. It's an accelerated 8-week course, so I put more straightforward questions because they, at that pace don't have the time to really let a lot of the concepts marinate in the way you would in a normal semester. So this test is probably a little more straightforward. If you stick around and you wait for me to show you the exam I'm going to give in fall 2025, it's going to be spicier. Okay, but let's just jump right in. Solve the following problems. Determine whether the given vectors are orthogonal, parallel, or neither. Justify your answers. So when you look at two vectors to determine whether they're orthogonal, parallel, or neither, checking orthogonality is pretty easy. You just make sure that the dot product of the two vectors is 0. To confirm whether or not they're parallel, you have a couple ways, but the easiest is you just check if they are scalar multiples of one another. And then if neither of those two cases are true, then you just say they're not orthogonal or parallel, neither. Okay, so let's look at these two vectors, A and B. Let's just take their dot product. That seems to be the easiest thing to do first. So 9 times -2 plus 3 times +6 gives me, lo and behold, -18 plus 18, which is 0. So these two vectors are orthogonal. And I did forget to mention, if you need like a recap of any of the concepts covered in this unit on this exam, that I've linked all the video lectures in the description below. So you can just check those out where I'll explain what orthogonal means or dot products, etc. Okay, next two vectors, let's check their dot product. So A dotted with B, that's going to be 4 times 3, so 12. 5 times -1 minus 5 minus 10. That's 12 minus 15, -3. Okay, so they're not orthogonal. Now let's check, are they scalar multiples? So in order to check that, you can just mentally do it. You could also just take ratios, right, of the corresponding terms in the components. So 3 divided by 4 versus -1 divided by 5 versus 5 over -2. No, we don't have a common ratio. So not parallel, not orthogonal. It's like so much writing, oh my God. Okay, so this is a neither. Neither. Good. Let me box the first one so there's no confusion. Okay, moving on. Here we have two vectors, A and B. Let's check their dot product. So -8 times 6, -48, minus 108, minus 12. I mean, they're all negative, so who cares what it is? It's not 0, so not orthogonal. Now let's see, are they scalar multiples of one another? You can do the same common ratio trick. So you just check, okay, 6 divided by -8, -9 divided by 12, and -3 over 4. Yes, those all reduce to the same ratio, -3 over 4. So that means these two vectors are scalar multiples. Woohoo! So that tells me these two vectors are parallel. Beautiful. One more. Let's check their dot product. So 3 times 5, 15, minus 9, minus 6. Oh, there we go, 0. So these are orthogonal. Okay, beautiful. Now, next example, or next part of the problem asked, find the scalar and vector projections of B onto A. So this should have been just straightforward, free points, as long as they remembered how to compute each of them. So the scalar projection we write as comp, because it's the scalar component basically, of vector B along A. So the vector that you're projecting onto goes at the bottom, looks like a subscript, and then the vector that you're projecting is the argument basically. And the way we compute it is we take A dotted with B and then divide by magnitude A. This quantity should be a scalar because it's a scalar projection. So let's dot these two vectors. A dotted with B is going to be 3, -3, 1, dotted with 2, 4, -1, over magnitude A is going to be square root of 9 plus 9 plus 1. So what's this going to give us? 6 minus 12 minus 1 over square root of 19. So negative 7 over rad 19. And I've told them many times you don't really need to worry about rationalizing denominators. It's not a big deal here. Okay, now we need the vector projection of B onto A. So when I teach them about vector projections, I emphasize it's just the scalar projection made into a vector in the direction of A, but we want to preserve the length, right, of that scalar projection. So you take your scalar projection that we just computed and you send it along vector A, but in order to preserve its length, we need to make sure vector A is a unit vector. That's why we divide by its magnitude. The formula is sometimes written differently, but if you think about it this way, it's kind of easier to remember and it conceptually should kind of jive with you better. Okay, so then we have negative 7 over rad 19, because we already computed earlier scalar projection of B along A. And then I'm going to need to multiply that by vector A, 3, negative 3, 1, dividing by magnitude of A, which is rad 19. So then you're just going to have negative 7 over 19 times 3, negative 3, 1. I accepted that. That was full credit. Some people stopped there. I'm like, you know what? You live your life. Some people left just 1/19 out and made this negative 21, 21, negative 7. That was cool. And some people just distributed all the way through. That was wonderful as well. I'll say this. If we were to do something else with the vector, that's going to be the easiest form to work with it. Like say I wanted to cross or dot this vector with another vector down the road, having the constant outside just simplifies that computation. So that's my preferred version, but you do you. And please, if your instructor has a certain way they want the answer, do it. Make them happy. Okay, find a non-zero vector orthogonal to the plane through the points P, Q, R. So we need 3 points to uniquely define a plane. Now a plane extends forever, so this little image is not an accurate representation. It extends forever, but there's 3 points here, and they can uniquely define a plane. So how do I find a non-zero vector orthogonal or perpendicular to the plane? Well, I'm going to make a vector connecting these 2 points, PQ, in the plane. I'm going to make another vector connecting these 2 points, PR, in the plane. If I cross those vectors, the result is always mutually orthogonal to the 2 vectors that you're crossing. And then, come back. Okay, so then the result of that cross product is going to be a vector that's orthogonal to the plane. Pretend that's coming out away from the plane. Okay, so first let's form those vectors PQ and PR. Now, you didn't have to do PQ and PR. You can do any sort of combination that your heart desires, okay? So PQ, to form it, you take the corresponding coordinates and subtract them, right? Terminal minus initial. So 5 minus 3 is 2, 2 minus 1 is 1, 4 minus 1 is 3. PR is going to be 5, 4, 2. So now if I cross these vectors, PQ crossed with PR. Now I show my class how to do this without having to write out, the matrix and do the determinant. You just imagine that there's I hat, J hat, K hat here, and then you go about finding the determinant. So it would be 2 minus 12, so that's negative 10. Then again, so here's J hat in your mind. You don't have to write it. So you eliminate that column, that row, and then don't forget to add a negative. So it's going to be 4 minus 15 and make it negative. What I do is I just multiply and subtract in the other order. So that automatically will change the sign. So I do 15 minus 4, and then that's 11. And then again, you're imagining there's K hat here. Eliminate that column, eliminate that row. 8 minus 5, 3. Boom. So it just saves time. I mean, we're going to be crossing vectors so much. So that's it. That's a non-zero vector orthogonal to the plane. There it is. So cute. Okay. Now it asks for us to find the area of triangle PQR. Now here's the thing. I'm just going to draw this as two-dimensional picture. So here's P, here's Q, here's P, here's R, okay? And we know that these vectors define a parallelogram, okay? And the area of the parallelogram is the magnitude of the cross product of the two vectors that define that parallelogram. So if we want the area of just triangle PQR, just this portion here, that's going to be half the area of the parallelogram. Okay, so then I just need to find half the magnitude of this vector that we have from part A. So that's going to be 1/2 times the square root of 100 plus 121 plus 9. So that's going to be 1/2 square root 230, which doesn't simplify. So let's just leave it. Rad 230 over 2. Okay, beautiful. Okay, one more, very similar kind of thought process. Find the volume of the parallel pipette with adjacent edges PQ, PR, and PS. So these 4 points, so long as they're not coplanar, will define a parallel pipette, which would have non-zero volume. So in order to find it, you just have to find the absolute value of the triple scalar product. And it really doesn't matter the order in which you make the vectors again, because we're taking absolute value anyhow. So I'll make the vectors PQ, PR, and PS. I'll make PS over here. So remember, the triple scalar product is when you cross two of the vectors and then you dot that with the third. And then for volume of a parallel pipette, well, we just have to take absolute value just in case it comes out negative. So you can do it in any order you want. You can mix them up. Because we're taking absolute value and dotting at the end, it doesn't make a difference anyhow. Okay, so PQ, these are different points than earlier, so we have to do this over again. 422, PR is 33 negative 1, and then PS is 551. Okay, so let me cross these two guys. I'm going to do the shortcut in my head. Yes, so I go, this column's gone, this row's gone. -2 minus 6 is -8. Then I go, this column's gone. IJK hat is gone. I'm just imagining, 6 minus -4, that's 10. And I don't talk it through like this. I just boom, boom, boom normally when I'm by myself. This is gone, this is gone. 12 minus 6, 6. Okay, so then volume is going to be absolute value of -8, 10, 6, dotted with, there's PS, 551. And you don't always need the absolute value, you'll notice. I think this is positive anyways, right? So -40 plus 50 plus 6, yep. So this is 16. This is a volume, so it's 16 units cubed, but they didn't have to add that. Just be aware. Okay. Here we go. Now moving on to the more interesting portion of the exam. Calculate the requested distance. You must show all relevant work justification in order to receive full credit. Simply using a memorized formula will result in a score of 0. That's what's up. Okay, so find the distance between the parallel planes 2x minus 3y plus z equals 4, and then there is a typo. 4x minus 6y, right? Otherwise, they're not parallel. Plus 2z equals 3. Okay, so let me draw a picture as part of the justification. So we want the distance between these two planes. I'll call this plane 1. This is plane 2. So we can extract the normal vector to plane 1 here by looking at the plane equation. Normal vector 1. Normal vector 1 has components 2, -3, 1. And then normal vector 2 for my second plane has components 4, -6, 2. And we can see that these planes are parallel because the vectors that are normal to them are scalar multiples of one another. Okay, now how do I find the distance between these two planes? And when we say distance, we always mean shortest distance. Okay, so here's the idea. We're going to take a point on this plane. We're going to take another point on this plane. We're going to make a vector. We're going to connect them. Okay. I just connected them willy-nilly. So the length of that vector will not necessarily give me the distance unless I'm lucky and I happen to pick them in just the right spot. So what I need to do then in order to find the distance once I've made this vector that connects the two planes is project it along either normal, and then that will give me the distance. So I'm going to find, let me summarize for you. I'm going to find the distance by taking absolute value, just in case it comes out negative, of the scalar projection of that vector PQ along either normal. I'll just do normal 1 because it has smaller numbers. Okay, you could also project along normal 2. It doesn't matter. So I'll repeat. You connect the two planes, and then what I want to do is project this vector along either of their normals, and when I find the scalar projection of that vector, that will give me the distance between the two planes. Okay, take absolute value just in case it comes out negative. Okay, so I need a point basically on each of the planes in order to connect them and to make that vector PQ. So just look here, pick whatever numbers you want for X and Y and solve for Z, or you can mix it up however your heart desires. Let's just say point P has components 0, 0, 3 halves. I'm not interesting. And then point Q, I'm going to come over here to this plane. Try to make it cute. Let's just do 2, 0, 0. Do you like that? If not, pick different ones. It doesn't matter. So beautiful. Like, you have so many options. If you do the math correctly, tons of different ways to, knock it out. Okay, PQ will have components 2, 0, negative 3 halves. Great. So the distance now is going to be absolute value. This scalar projection you find by taking the dot product of the two vectors, PQ and N1, and then I divide by magnitude N1. So that's going to be square root of 4 plus 9 plus 1. Perfect. So what is this going to be? 4 plus 0 minus 3 halves over rad 14. So 4, that's 8 halves, minus 3 halves is 5 halves. So 5 over 2 rad 14. Perfect. How was that? Fun, right? Not like a really laborious process. No. Okay, determine whether the lines L1 and L2 are parallel, skew, or intersecting. If they intersect, find the point of intersection. Okay, so here are my two lines. Line 1 has as its direction vector, I'll call it V1, components 1, negative 2, negative 3. I'm just looking at the coefficient of t from the parametric equations. Line 2's direction vector, V2, has components 1, 3, negative 7. So I can see right away these two vectors, they're not scalar multiples, which means the direction vectors are not parallel. Therefore, the lines are not parallel. Okay, so that's done. Now, the next thing before I can determine whether they're skew, I want to see, do these lines intersect? Okay, so that would mean if they intersect that they share an ordered triple, that they have an XYZ in common. So I'm going to check, does t plus 2 ever equal s plus 3? Does negative 2t plus 3 equal 3s minus 4? And does negative 3t plus 1 ever equal negative 7s plus 2? I don't know. Now here's the thing. I have 3 equations and only 2 unknowns. That's more equations than unknowns. So what I'm going to do is just work with 2 of the equations at a time, solve for s and t, and then take that result and verify that it works in the 3rd equation. If it doesn't, then there's no solution to my system. So let's see, how do we feel about this system? Looking at the first 2 equations, I want to do elimination. Let me just double the first equation. 2t plus 4 equals 2s plus 6. And then let's leave this guy alone. Negative 2t plus 3 equals 3s minus 4. Okay. Then this is 7 equals 5s plus 2. So 5s is 5, so s is 1. And then just mentally, if s is 1, t plus 2 is 4, so t is 2. Okay, so this solution came from working with the first two equations. Let me check now if they work in the equation for z. So negative 3 times 2 plus 1, does that equal negative 7 times 1 plus 2? Negative 6 plus 1, it does. So that means, yes, the two lines, they indeed intersect. Now I need to actually find the ordered triple. So it's up to you. You could take t equals 2, plug it in here, or s equals 1, plug it in here. Doesn't matter, they intersect, so you'll get the same ordered triple. And they intersect at 4, negative 1, negative 5. If we couldn't find where they intersect, then we would say they're skew. Okay, and it is important to verify that they're parallel, that they're not parallel, excuse me, because parallel lines can intersect at infinitely many places if they are the same line. So you should have checked all components. I think that's where maybe some people miss points. Okay, find the equation of the plane that passes through the point 3, 5, negative 1, and it contains that line, x equals 4 minus t, y equals 2t minus 1, and z equals negative 3t. So this plane contains this point, 3, 5, negative 1, and then it also contains some line whose parametric equations they gave me. I'll call my line L. So think to yourself, what do I need again when I write the equation of a plane? I need a vector normal to the plane, okay? So how do I get a vector normal to the plane? Well, if I have two vectors in the plane, I can cross them and find a vector normal to the plane. Do I have two vectors in the plane? Well, let's see. They gave me the equation of this line that's in the plane. The direction vector of that line has components negative 1 to negative 3. And v is in the plane, is it not? Great. I just need one more vector in the plane. I can cross it with v, and boom, I'll have a vector normal to the plane. So how do I get another vector in the plane? I have this point in the plane. Oh, I wish I had one more point in the plane. I'm just going to come to the line and plug in whatever I want for t, and I will have another point in the plane. Perfect. Okay, so I like to plug in nice numbers. Let me plug in t equals 0. You don't need to, but plug in t equals 1 if you want. Then you get 4, negative 1, 0. This point is in the plane, and it's on the line, but who cares? So let me make a new vector. I'll call this guy Q. P is over here somewhere, right? Let me make a vector QP, so we don't have negative leading component. QP has components 1, negative 6, 1, and it is in the plane. So boom, vector V is in the plane. I don't know where V is. It's somewhere on the line. QP is in the plane. QP. Cross them, and we're going to get a vector normal to the plane. So my normal vector to the plane would be V crossed with QP. So V is negative 1, 2, negative 3. I want to cross it with 1, negative 6, 1. And I'm just imagining I had j hat k hat on the top, and I get negative 16, negative 2, 4. So I'm going to try to write the equation of a plane. Let me cutesify this. What we can use instead is if I divide everything by negative 2, 8, 1, negative 2. That's still going to be normal to my plane. It's just fully simplified, reduced. You can't do this when you're asked to find a distance. But if you're just finding the equation of like a plane or a line, it's totally cool. Reduce your little heart out. If you reduce when you're finding a distance, now you're scaling down the distance, right? You're not preserving that scalar quantity. That's why it's a problem. So that's my normal. I need a point on the plane to write the equation. You can use this one. You can use this one. Have at it. I'll use the one they gave me. So 8 times x minus 3 plus 1 times y minus 5 minus 2 times z plus 1 is 0. So you end up with 8x plus y minus 2z is 31. Beautiful. Okay, halfway through. Good. So sketch and identify the given surface. Include traces of each in each of the 3 coordinate planes. Your graph must be neatly labeled in order to receive full credit. So right off the bat, let's identify this is an ellipsoid. And let's put it in standard form so we can graph it. So it always has to equal 1. So I'm going to divide everybody by 900. So we'll have x squared over 9 plus y squared over 25 plus z squared over 4 equals 1. Now let me graph the traces in each of the coordinate planes. So in the xy plane, that would mean z is 0. So we would have an ellipse. X squared over 9 plus y squared over 25 is 1. So the x-intercepts would be at 3, negative 3. The y-intercepts 5, negative 5. And it would look something like this. Here's my x-axis, here's my y-axis. Now in the yz plane, that means x is 0. Again, we get a cute little ellipse, y squared over 25 plus z squared over 4 is 1. So I'll say this is the y-axis, this is the z-axis. Y-intercepts are 5 and negative 5, and then z-intercepts 2 and negative 2. And then lastly, we have the good old xz plane. I mean, you could do it in whatever order, it doesn't matter. Y is 0. Again, an ellipse, so you'd have x squared over 9 plus z squared over 4 is 1. This is x, this is z. X-intercepts are plus or minus 3, and z-intercepts plus or minus 2. So now it's just a matter of translating everything to the 3-dimensional coordinate system graph. So the x-intercepts I need are 3 and negative 3. And the y-intercepts 5 and negative 5. 1, 2, 3, 4, 5. Okay, so let's draw that trace in the xy plane. Then in the yz plane, we have to go up to 2, down to negative 2. Here and here, YZ plane coming in hot. Boom, boom. And then the only one I'm missing now is the XZ plane. So that one, I already have the points. I'm just going to connect and make another trace. So there it is. A little deformed. Shall we shade it and try to make ourselves feel better? You do you. As long as everything was labeled correctly, the intercepts, and for the most part, the traces looked decent. They were fine and had to identify. Okay, moving on, evaluate the integral. We have a vector valued function being evaluated from 0 to 1, 9t squared minus 5 I hat plus 8t over t squared plus 1 j hat minus t over rad t squared plus 1 k hat. And this is all evaluated from 0 to 1 with respect to t. So as long as the notation was correct, if they did u sub, they needed to change the limits of integration. Or maybe you could just get away with not doing u sub for some of it. That's fine too. So here we go. I'm just going to actually start evaluating. So we can write it as 0 to 1, 9t squared minus 5, 8t over t squared plus 1, and negative t over rad t squared plus 1 dt. Okay, so taking the antiderivative of the first component, you're going to get 3t cubed minus 5t. The second one, if you did a u sub, then you would need to change the limits of integration, so you would need to break that one off separately. I don't feel like doing that, so I'm just going to do it in my head. If u is t squared plus 1, du would be 2t dt. I have 4 times that. So we have 4 ln absolute value t squared plus 1. And then same thing here. If u is t squared plus 1, du would be 2t dt. I have a negative, so I'll pick up a negative 1/2. And then when you take the antiderivative of square root in the denominator, that's to the negative 1/2 power. If I add 1 to the exponent and divide by the new exponent, you'd have 2 times rad t squared plus 1. And then all of this gets evaluated from 0 to 1. Okay, so then we're going to have, if I plug in 1, this will just be 3 minus 5 minus 0. 4 ln 2 minus 4 ln 1, and that's 0. And then 1/2 and 2 cancels. So I just have negative rad 2 plus rad 1. Okay, then just clean up. So this is going to be negative 2, 4 natural log of 2, and 1 minus rad 2. I would say the biggest problem on this question was that people did u sub and didn't change the limits of integration, and then they said, oh, but I went back to t. Yeah, but you can't have an integral where you still have original limits that are for t, different variables, a function of u. If these do not match, that's not a well-defined integral. You can't just say, I'm going to go back, it'll be okay. No, it's not. It's not okay. Especially because later on when we start doing double, triple integrals, you're going to be changing coordinate systems. Limits of integration immediately need to be switched. You're not going to go back. Okay, it's serious business, guys. It's serious business. Find the arc length parameter along the curve from the point where t equals 0 by evaluating the integral from 0 to t of the magnitude of v of u du. So here's our vector valued function r of t with components e to the t cosine t, e to the t sine t, and 6e to the t. So we know absolute value or magnitude of v of u is magnitude of r prime of u. So that's what we're going to have to find. So first let's find r prime, and then I'll change it to be a function of u when I put it in the integral. So we need to do product rule. It's going to be e to the t cosine t minus e to the t sine t. Next component, e to the t sine t plus e to the t cosine t, and then 6e to the t. Now to get the magnitude, be kind to yourself. Take the e to the t out, because you see everything contains e to the t. Who wants to be squaring it all in there if you don't have to? And then when you take the magnitude, it just comes along for the ride. I've shown this before in the lecture. So you can just keep e to the t and then do the magnitude of the rest of the components. Come back. There we go. So if I square the first component, you guys, we're just going to get this show on the road. It's going to be cosine squared t minus 2 cosine t sine t plus sine squared t. Square the next component, sine squared t plus 2 sine t cosine t plus cosine squared t plus square the last component, 36. Look at this. Look at this gorgeousness. These guys cancel. Love it. This is 1 plus 1, so that's 2, plus 36, 38 last time I checked, so e to the t rad 38. Okay, so then our arc length parameter, s of t, is defined to be the integral from 0 to t. Now, if t is one of your limits of integration, you can't be integrating a function of t, so that's why we switch to some dummy variable. Usually we use u, e to the u rad 38 du. And then from here, you're just footloose and fancy free. Rad 38 e to the u, evaluated from 0 to t, is going to be rad 38 e to the t minus 1. And that's it. They didn't have to actually find the arc length parameterization. Woo. For the vector valued function, just stop there. Okay, I think the most problematic thing here was the notation, or some people didn't do the product rule. Okay, so find t, n, and b for the given space curve. Let me rewrite the vector valued function, not using our unit vectors. So first component is ln cosine of t plus 6, 1, and then 2 plus t. So remember t, our unit tangent, is defined to be r prime of t divided by, make it a unit vector, magnitude r prime. So here, let's go find r prime. Let's do it. Derivative of ln cosine t is going to be negative sine t over cosine t, 0, 1. So that's negative tan t, 0, 1. Now, magnitude of r prime of t is going to be square root of tan squared t plus 1. So that's square root of secant squared t, which technically is absolute value of secant t. And then this is where you use the fact that t is between negative pi over 2 and pi over 2. That's quadrants 1 and 4. And in quadrants 1 and 4, secant and cosine are positive. So then I know I can drop the absolute value bars with a clean conscience. So then my unit tangent is negative tan t, 0, 1, divided by secant t. But that simplifies. That's the same as multiplying cosine t through the vector, which I'll rewrite tangent now as sine t over cosine t, 0 and 1. And this becomes, that's right, negative sine t, 0, cosine t. So this is my unit tangent. Cute, 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 cute. We love it. Now to get the unit normal. Unit normal is t prime of t. Make it a unit vector. Divide by magnitude of t prime. So t prime is going to be negative cosine t, 0, and negative sine t. Hopefully you can see the magnitude of this vector is stunning. It's 1, right? Cosine squared t plus 0 plus sine squared t, 1. Okay, cool. So that means my unit normal is the same as t prime, because t prime was already a unit vector. Fabulous. Okay, and then how do you get the binormal vector? B of t, you cross t and n. And automatically it's a unit vector. I prove why in the video lecture. Anyways, I'm going to cross them in my head. I know they're not stacked, but I'm pretending they're stacked, and I'm pretending there's an I hat, j hat, k hat. So this will be 0, negative cosine squared t minus sine squared t, and 0. The order does matter. B needs to be t crossed with n, not the other way around. If you switch the order, then the sign will be off. So this is 0, negative 1, 0. Hopefully that was free points for everybody. Handing out points on the sidewalk, like popsicles on a summer day. Okay, last one. At what points does the curve intersect the paraboloid? So the curve is defined by a vector valued function with components t, there's no j, and k, 2t minus t squared. So basically, if you wanted a parametric representation for this curve, x is t, y is 0, and z would be 2t minus t squared. So to see where it intersects the paraboloid, just substitute in the parametric representation for that curve for x, y, and z. So z is 2t minus t squared. That equals x squared plus y squared. So then I have 2t squared minus 2t is 0. I can factor out a 2t, and then I have t minus 1, right? So either t is 0 or t is 1. So what points would that correspond with? Just come right here. But it asked for points, right? Technically, that function is making a bunch of little position vectors that trace out a curve, but I'm going to write them as ordered triples, not vectors in 3 space. So if t is 0, you have 0, 0, 0. And if t is 1, then you have 1, 0, 1. So those are the 2 points. Beautiful. Find a vector function that represents the curve of intersection of the cone and the plane. Okay, so to find their intersection, you would just set them equal to each other, and I have z as a function of x and y explicitly. From here, we have to come up with, what's going to be a nice parameterization to describe this curve of intersection. So let's clean up a wee bit more. Can I solve for one of the variables in terms of the other? Let's square both sides. Don't forget this is going to be 1 plus 2y plus y squared, yeah? Good. Those cancel. Looks like the easiest variable to solve for would be y. So 2y is x squared minus 1. So y is 1/2 times x squared minus 1. So here's the thing. When you're trying to find a parametric representation, you need x, y, and z all in terms of some parameter, t. It looks like if I can define y in terms of x, I should just let x then be my parameter, let x be t, then y would be 1/2 t squared minus 1. See how beautifully that worked out? And then you just have to define z in terms of t now. So you go, do I want to do this one or do I want to do this one? The plane equation looks better. So the plane equation is 1 plus y, which is 1/2 t squared minus 1/2. So this is positive 1/2 plus 1/2 t squared, which is 1/2 times t squared plus 1. So there we go. I'm going to write it now as a vector function as the problem asked. So r of t is t 1/2 times t squared minus 1, and then 1/2 times t squared plus 1. Done. Okay, cute. Now there were 2 little extra credit proofs. So let P be a point not on the line L that passes through the points Q and R. Show that the distance D from the point P to the line L is given by the magnitude of the cross product of A and B divided by magnitude of A, where A equals QR and B is QP. So let's draw. This isn't like such a super formal proof as long as they had a good diagram going. Here's the line L. It passes through the points Q and R. So we're going to make a vector QR. And then the point P is somewhere over here. The vector QP is called B. This one's A. We want this distance here. There are a couple different ways they could have shown, actually 3 different ways they could have done this one. I think the easiest, most popular one was people made a parallelogram. Okay. And we know we can find the area of the parallelogram. I've already discussed it in a previous problem. The area of that parallelogram is equal to the magnitude of the cross product of the 2 vectors that define it. So it would be the magnitude of the cross product of A and B. Well, we also have another formula for area of a parallelogram. It's base times height. The base is given by magnitude of A, and in this case, the height of that parallelogram is D, the distance. So then you're literally done. So just divide by magnitude A. The distance equals magnitude of A cross B over magnitude A. That's it. Too easy, huh? Yeah, a lot of people got this one. Okay, the next one, I think only one person got it right. What a genius. Show that if a particle's velocity vector is always orthogonal to its acceleration, then the particle's speed is constant. So let's let r of t be the position function for a particle. Then r prime of t would be the velocity, and then r double prime of t would be acceleration. So they told us to assume that the velocity is always orthogonal to the acceleration. So what that means is we know velocity and acceleration are always orthogonal. So their dot product must always be 0. If that's the case, then 2 times, let me put of t, r prime of t dotted with r double prime of t would also be 0, right? I just doubled everything. Now, remember, like, you know how 2x is x plus x? I'm going to do that over here on the left. So I could write that as r prime of t dotted with r double prime of t plus r prime of t dotted with r double prime of t. That must be 0. And then I want you to observe this is the derivative with respect to t of r prime of t dotted with itself. It's the product rule. So when you do the product rule, leave one alone, take the derivative of the other one, plus derivative of this one, and then leave that alone. And dot product's commutative, so we're good. Okay, well, what does that mean? That means if we integrate both sides with respect to t, Well, according to the fundamental theorem of calculus, that integral and the derivative would undo one another. So this is just r prime of t dotted with itself equals antiderivative of 0 is just some constant. I'll call it c squared. And then remember, by definition, we looked at how if you have some vector dotted with itself, it's equal to the magnitude of that vector squared. If you forgot, go back to the lecture on dot product. I show why. And so then we're pretty much done. That means magnitude of r prime of t is equal to just c, some constant, and magnitude of r prime of t, that's how we define speed. Beautiful. So that's it. That concludes the video, solving the exam. I know it was like rapid fire at the end. It's kind of over it, guys. Sorry. So if you need a more in-depth explanation, like I said, check out the video lectures in the description. My class told me I'm boring in my videos compared to how I am in class. So I'm sorry. I'll try to be more interesting. This video, though, I'm not trying to teach you guys as much as I just wanted to get the solutions out there for the class in case they wanted to look over where they made mistakes, or if anyone's going to study for like an upcoming exam, I would say if I were you, I would pause the video as soon as I show the question, try solving it, and then look at my solution, you know. But if you need like a cuter, in-depth explanation, obviously this was not it. This was just rapid fire solving. So that's it. It's good. It's fun. I like solving exams fast. When I was a student, I'd be like, ooh,